Good morning, people. Welcome to the end of class, really. So I wanted to briefly explain the last lab that you have to do. There are four parts to it, and the last two are pretty self-explanatory, and I think you'll get through them just fine. The first two, I think, require a little bit of explanation. So I wanted to let you know that you're working first in part A with stable isotopes. And stable isotopes are very simple in terms of the basic science. An isotope is an atom that has more or less neutrons than is normal. So, for example, or not for example, in this lab, you'll be working with oxygen 18, which just has two more neutrons than the normal oxygen 16. And when oxygen 18 bonds with two hydrogen molecules, it makes heavy water. So this heavy water versus light water gets sorted out on the convection cells we talked about in class. So at the equator, when the sun is beating down on really warm water, the sun will preferentially evaporate light water, which is to say water that has oxygen atoms that have 16 neutrons, and leave the oxygen 18 or heavy water behind. And now when the water goes up as vapor into the atmosphere, when it rains, any oxygen 18 that was evaporated will preferentially fall as rain. So atmospheric processes actually sort this water, and so by the time you get to the North Pole or the South Pole, you have really, really light water, which means that it's pretty much all oxygen 16 in the water. This also happens when you go up a mountain, which is where glaciers are, right? So as you go up the mountain, there's evaporation at the base of the mountain that will fall as rain or snow as you go up the mountain, and the same thing happens. Light water is preferentially evaporated and heavy water preferentially falls. So for part A of the lab, all you're doing is looking at, if you look at figure 18.1, you will see that there is a graph that shows the water, or the oxygen 18 that is in the glacier. It's oxygen isotope particles. The y-axis goes from 1000 year AD up to 1980, and the x-axis, which is at the top, is del O18 per mil. Don't have to worry about the details of that. Just understand that the lower that number goes into the negative, so you see there's some things that are about negative 21, the colder it is on Earth at that time as recorded in the ice. And the less negative, so you see that as the light colored parts of the graph that are going up towards negative 16, that is more weighted with oxygen 18, so it's warmer on Earth. So if you look at the period of time, for example, from about 1600 to about 1900, it's colder on Earth because sorry, did I say that wrong? There are more negative values, which means that it's more oxygen 16. And the closer it goes to the negative 16, the warmer it is and the more O18. That's correlated with a second graph that shows essentially a volcanic eruption as evidenced by ash that's in that ice core. And so you will do a series of questions about what happens in response to regional volcanic exercise or eruption, sorry. So the second part of this is a graph that is 18.2. There are four ice cores that you're looking at. And what you're looking at the bottom is the hatched stuff is rock. And then the stuff above that is the glacier and the sediment. And so A, B, and C are, I think, let me see, sorry, looking at the graph at the same time. A, C, and D, no, B, C, and D, apologies. B, C, and D are from 1976. So scientists went to the summit, the middle, and the South Dome in 1976 and took these ice cores, and from this got the signatures that you see in cores B, C, and D. Then scientists returned to the summit in 1991 and took another core. So B and A are the same exact location, but just advanced in time when you're looking at A. And So you're going to answer a series of questions about what happened in the intervening years. The key to this is the dashed line that hits the summit dome in 1991. That's the melt line. So anything below that melts seasonally and sends water infiltrating or percolating down into the subsurface. You see that in 1976, it was quite a bit lower. It was about where the middle dome is. And since the melt line rose, you can intuit that the area got warmer. So you'll answer a series of questions about what that means. And do feel free to email or call, request a video conference, and I can walk you through that further if that doesn't make sense. But it is a complicated graph. It takes a little bit of time to look at and dissect, but once you understand the basics of it, you should be able to answer the questions. So this is a lab. I didn't want to make you buy a lab book, so this is kind of a dark photocopy. I tried to do the best job I could. The next thing you're doing is looking at glacial retreat. And I recommend watching Chasing Ice if you haven't done so already, because this is exactly what the film photo documents. But you look at 18.3, and the retreat, if you look at the second part of the figure, is about where that farther up white horizontal line that's just an artifact of photocopying is. So you're going to answer questions to the best of your ability about the retreat of that glacier. And then when you look at figure 18.4, it's the same thing. You see there's a lake that was there in 1991. That's the meltwater of the glacier. And you see the figure, again, I recommend Chasing Ice, the outline of the glacier from 1963 to 1991. So you're going to do as best you can to figure out the rate of retreat. The way you figure out the rate of retreat is to take a ruler. You have a scale right there in figure 18.4. And to show what the overall retreat in meters is, and then divide that by the amount of time that this went on. So you'll answer 3 or 4 questions about that. And then going into part B, I think that you can pretty much figure that out. The first part asks about figure 8.5, which is looking at ozone, looking at chlorofluorocarbons, and looking at chlorine that's been stripped from the chlorofluorocarbon by ultraviolet radiation. So you'll answer those questions, and then there's a graph on the decline of ozone. And this is actually a good news story, because you see that ozone as of about 2000 is starting to rebound. There's one question, and it's question 4, that you wouldn't know how to answer, so you just have to write that down. Ozone is a gas, and so it's very difficult to measure gas. The way that we measure ozone in the stratosphere is by pretending that it is in liquid form, and we hold pressure and temperature constant. So you take that ozone that's up in the stratosphere, you bring it down to sea level, in theory, and you put it to 0 degrees Celsius. So the answer to question 4, which again, this isn't a critical thinking thing, you just have to look this up, is that 1 Dobson unit of ozone is equal to 1/100th of a millimeter of ozone at 0 degrees Celsius at sea level, so in liquid form. So you can go from there. 8 Dobson units is 8/100ths of a millimeter of ozone at sea level at 0 degrees Celsius. So you can put X in, that's what I did. X Dobson units equals 0.0x millimeters ozone at sea level. So there's that. The last thing that I wanted to let you know is that this lab is a couple of years old, and when you get to the part about the third assessment report for the Intergovernmental Panel on Climate Change, that's question number 11. We are actually on the 5th report that came out in 2014. And the URL that you see listed in the lab is still the same. So it's http://www.ipcc.ch. So if you go on that, you can see updated data. They're actually have finished convening to write the 6th report, but that won't be published until 2020. So you can get up-to-date data on there and look around at it. It also is referenced in the film Chasing Ice. The guy who is documented in that film actually went to the Paris convention and talked about the glacial retreat. So a neat thing to look at there. So that's the lab. And again, I have published the answer key. I'm asking you, please, Honor System, to not look at it unless you run into a big problem. I'm always available for a video conference or for email if you have any questions about the lab beyond what I just said. So have a good weekend, and I will see you sometime.